Hello calculus students. We're going to look at a few more examples of parametric calculus today. And I thought we'd start off by looking at the book's little bit about areas or surfaces of revolution in parametric coordinates. So you should have already looked and viewed the video on arc length in parametric coordinates. So now we're going to look at surfaces. I think surfaces actually are easier in parametric coordinates than they were in normal Cartesian coordinates. We'll see if you agree with me after this example, but I think you definitely will. So let's see what happens here. So it says in the book you can use the formula for the area of the surface of revolution in rectangular form to develop one in parametric. So the part that we just talked about in the last video examples or in class was that in parametric coordinates, this little guy right here is the equivalent of arc length if you integrate it from the beginning, or a, if a is the beginning value of the parameter t, and if b is the end value of the parameter t. I usually call this, t1 and t2. But there you have it. This is the arc length. Remember, in Cartesian coordinates, just to review, the arc length should be square root of 1 plus dy dx squared. And so we derived that this is what it turns out for parametric coordinates. All right, so what else do we have in here? Well, the only other thing we have is this 2 pi out here and g of t in here. So let's talk about what those are and why they make sense. So 2 pi r is what we're doing here. Because remember, if we think about a visual, we've got some curve. Let's just imagine something simple like that. What we've got to do if we want the surface of integration is maybe we're revolving it this way. So that kind of revolution. So if we're doing that and we're looking for the area of the surface on the outside of that region, then we've got to figure out the arc length, which I was doing in green, so I'll try to be consistent. Let's say we wanted to go from here to there. Then we'd have the arc length, that's why we had the green portions. And then you have to take that arc length and do the around process with it. So that's of course going to be the circumference of a circle, and you just have to figure out the radius of that circle, what that's going to be. So in this case, in the setup that I have where we're revolving around the x-axis, the radius is going to be this distance, which is of course the y distance. Well, the nice thing about parametric coordinates is of course that the y distance is split into the y coordinate, which in this, well, let me not draw over that, which in this setup is called g of t. So this is basically just, the y equation, which totally makes sense. That's the y equation. So that's for revolving about the x-axis. If you want to revolve about the y-axis and go the other way, then, you're going to have, I guess I can just draw it one more time since we're here. So we'll go over here and draw a curve, just a real similar curve there. And then we'll have the arc length that we want to revolve. Let's say this piece right here. And then we want to revolve it this way. So in that case, the r is going to be this distance, which is of course the x coordinate. So they have that labeled f of t here for the x part of the parametric equations. So I think you can see how surfaces are going to be easier in parametrics than they were in Cartesian. If they were difficult in Cartesian, I don't know. There sometimes can be some weird examples, but shouldn't be too hard. All right, so let's do an example. So let's say we've got the curve x squared plus y squared equals 9. That's a simple circle. Oh, I guess they already called it a circle. Cool. So we just got a very simple circle with radius of 3. So they want us to investigate this arc that they've labeled in black here. They say it goes from 3, 0 to 3 halves 3 root 3 over 2. They want us to find the area of the circle by revolving that around the x-axis. So that's going to be our r is the y. So we already know that the y equation in the parametric equation is what we want. So the question is, what are parametric equations, x and y? Well, we got to think about this. What is a circle? I think we've hopefully done enough examples of parametric for you to kind of know how to do that. So what was it for a circle? Didn't we go like x equals like sines and cosines, right? So it probably doesn't really matter. I'm just going to say x equals 3 cosine to be consistent with the book in case you're following along there. And then we're going to go 3 sine of t. It really doesn't matter which one of these we chose since it's just a circle. But you can see if you go x over 3 squared plus y over 3 squared, that's sine squared plus cosine squared, which is of course 1, and then you just multiply by your over 3 squared, which is, you'll get that 9. So I'm not going to show that in this case. But anyway, so those are the parametric equations which correspond to this Cartesian equation. Alright, so we wanted to do the arc length and to utilize our parametric equations to do that. So let's do it. So we're going to have 2 pi r, with the r being the vertical equation, and we're going to integrate that, so we'll put the thing we need to integrate inside. So the y for us is going to be 3 sine of t, and then in here, and we're going to go from t1 to t2, and in here we need to go dx dt squared plus dy dt squared. Let me get that down. Try to make it somewhat legible, and dt. Okay, so what are we going to have? I'm going to switch colors here just to make this a little nicer. So that's going to be 2 pi, and our first task is really to figure out what these values of the parameter are for these x and y coordinates. So I think the best way to tackle this is you can definitely experiment a little bit, and that's just the name of the game when you work with these other coordinate systems that you just don't have as much intuition with because you haven't been working with them for years like you have with Descartes' XY coordinate system. So don't get intimidated. The way I'm going to approach this one is I'm just going to focus on the x coordinates. I think you could also focus on the y coordinates, but I'm not as comfortable with this radical here, so that's why I chose to look at the x coordinates and just focus on my x equation and see what that runs from. I'm guessing the curve is going this way. But honestly, I'll find out as soon as I start experimenting. So we'll confirm that in a second. So we get x equals 3 for some angle. What angle might that be? I'm guessing that the angle is going to be 0, but it might be going the other way. So let's just check. So could we get 3 if we go 3 cosine of 0? Cosine of 0 is right here. That's the x coordinate right there, which is 1. So is 3 equal to 3 times 1? Check. So yeah, I think that that's going to go from 0. So I'm going to say 0 is time 1. Okay. And then I'm going to go and say, I'm kind of running out of space here. Let's scroll up a little. There we go. And say, well, how we get 3 halves? So we get 3 halves if we're at 3 cosine of what t value? So let's just see if we can solve for t there. So I'm going to divide both sides by 3. To kind of get rid of these, and so then I'll have 1/2 equals cosine of t, and I can just apply the arc cosine to both sides, so the arc cosine of 1/2, arc cosine lives in these two quadrants, it's positive over here, so that's going to be adjacent hypotenuse, that means this must be square root of 3, that means this angle dude in here must be 60 degrees or pi over, pi over 3. Okay, so I think that's our second value of the parameter is pi over 3. There we go. Alright, so then we've got 3 sine of t already. We need to figure out the dx dt and the dy dt. That should be super easy here. Dx dt is just the derivative of that equation up there, so it's going to be negative 3 sine squared of t. Well, let's just put it in here since I already have the negative. All right, plus the derivative of this one's going to be 3 cosine of t, and we're going to square that one dt. Alright, we just need to simplify, and hopefully the simplifying will go easily, and we'll be done with this problem. Now, my pi's are just looking ugly today. So we've got 3 sine of t times the square root, and inside looks like we have 9 sine squared, and 9 cosine squared. Beautiful. That's going to be an easy simplify, right? You can just factor out 9. And you get your identity for sine squared plus cosine squared. This should be over 3. Sine squared plus cosine squared, of course, equals 1. So that's just going to be the square root of 9. Beautiful, which is just 3. 3 times 3 is 9. You can bring that all out in front. 9 times 2 is 18, and then we've got the integral from 0 to pi over 3 of the sine of t, which is going to be what? Integral of sine is negative cosine, positive cosine. I'll think about it a second. I think it's negative cosine, so we're going to go negative cosine of t from 0 to pi over 3. That's going to be 18 pi times negative, what's the cosine of 60 degrees? Oh, we even have that triangle up here. We could just go right up to it, right? Cosine of that triangle is going to be 1/2. Great, so negative 1/2 minus a negative, and the cosine of 0 we just talked about was 1. So it's going to be 18 pi negative 1/2 plus 1. It's going to be 18 pi times 1 minus a half is a half. Okay, so that's 9 pi. Of course, we want to think about what we were doing here. We're actually getting the area of this blue shell or surface that you can see pictured in our problem from the book. So that's going to be 9 pi. I'm just going to specify that that's units squared for area. All right, I think we'll move on and look at some other examples from the book now. The second example I wanted to look at says to find the equations of the tangent line at the point where the curve crosses itself. We definitely need to be competent enough to find tangent lines on the AP test for any coordinate system, be it Cartesian, polar, or parametric. So we definitely want to be able to find tangent lines in those different coordinate systems. So I thought this would be another good example to pursue. So here's our two curves. First, it says where the equation crosses itself. So perhaps we should figure that out first. Well, you know, I think I'm going to need the slope, so maybe I'll do that first, and then we'll bring up our calculator and figure out the tangent line. So let's do dy dx. So to do dy dx, we're of course going to need dx dt. So I'll do that underneath here, which is 2t minus 1. Nice easy derivative. Dy dt will also require. So dy dt is going to be 3t squared minus 3, another easy derivative. So that means dy dx is going to be the ratio of those two with the y at the top and the x1 on the bottom. Now it looks like I might be able to simplify by like pulling out a 3 and doing difference of squares and stuff on top, but I don't see anything that's going to cancel. You always want to try to cancel this down if you can, especially of course if you're going to take a second derivative where you need to go the derivative of this guy on top and then another dx dt derivative on the bottom. But we just need a tangent line, so I think I'm going to stick with that. So let's go to our calculator and see if we can figure out where this curve crosses each other. So that might be nice, because that's pretty essential for our problem. So we might do this with a little experimentation. We'll see what happens. So first I'm going to change the mode of my calculator to parametric. And then if I hit y equals, it should be in parametric. So I'll stick my equations that we had in there. So we had t, let's see, we had, I think I'm just going to use the calculator, t squared, then minus t is x, and t to the third minus 3t minus 1. Let's look at our window here. The step is pretty small. I'm going to, well, change it to 0.3. I'm just going to go back in time a ways and forwards in time a ways just to see if I can see a good range of values here. Let's just try that. Okay, so there we can see a pretty good view. It looks like the curve is crossing itself somewhere around here. I'm going to zoom in with the x's and y's and make that a little bit easier. So x, how about we just go from -1 to, uh-oh, there we go, oops, we need this small negative picky calculator guy. Now let's go to 5, and let's go, let's see, negative, let's see, it doesn't like that negative. Let's do this small one, 2 to 5, definitely, I'm going to go 3, graph there. Okay, so it looks like it crosses at the spot, looks like x is 2 and y equals 1. So let's try to just work with that and see if we can figure out what t might be for that case. So we'll kind of experiment again, but let's just try to figure that out a little bit now. So it looks like they crossed themselves. Let's just kind of draw the graph up here like what we saw. We saw something, what was it? Something like that. So it crossed itself, it looked like at about 2, 1. So we're finding some tangent lines there. Looked like it did something like this. Okay, so we should have one that's got a positive slope probably, and one that maybe has a positive slope, maybe negative. I don't know, my picture's not that great. So the x, y coordinates we're looking for, though, are 2, 1. Alright, so let's focus on that and see if we can solve. So let's see. If x is 2, then we have 2 equals t squared minus t. And then y is 1 equals t cubed minus 3t minus 1. So what would make both of these equations true? So here we have 0 equals t squared minus t minus 2. Oh, that's factorable. Very nice. So that would be t minus 2 and t plus 1. So that's t equals 2 or negative 1. I'm guessing those are the 2 time values. Since we can only see 2, that should be good. We don't even have to worry about trying to solve this cubic equation. So don't need that guy. Okay, so let's write that down to keep track up here. That the 2 values that we have are probably t equals 2 and t equals negative 1. We could, of course, go back to our calculator and check those if we weren't sure, but I'm pretty sure that that's good enough for now. So let's go ahead and start constructing our tangent lines. We're going to, of course, need slopes for those. So I'm going to switch to blue just to distinguish here. So let's find dy dx evaluated at t equals 2 first. So you can really see the advantage of Leibniz notation here with the evaluation in parametric land. So at t equals 2, that's going to be 3 times 2 squared minus 3 over 2 times 2 minus 1. That's 3 times 9. It's 27 minus 3. 4 minus 1 is 3, so it's going to be 24 over 3, slope of 8. I'm guessing that's the slope of this really steep line right here, but I could be wrong. My graph wasn't perfect. We'll check it when we're done. Okay, so I've got that tangent line. Let's do the other one. I've got that tangent line's slope, I should say. So the other guy is going to be at negative 1. So that is going to be equal to, let's see, 3 times negative 1 squared is 1 minus 3. And then we've got negative 1, so it's going to be negative 3 on the bottom. So 3 minus 3 is 0 over negative 3. So it's slope of 0. So is that guy really 0? I'm a little bit skeptical on that guy. Go back and look at our curve real quick. Oh, it does look flatter. You see how it looks flatter there? This guy does look steeper. I think we're good to go. So we should be good. Let's actually create our tangent lines and be done with this problem. So this guy is going to be y minus, we're going through the point 2, 1, right? So it's y minus 1 equals the slope times x minus 2. So that's going to be y equals 8x minus 16 plus 1. So that's going to be y equals 8x minus 15. So I think that's probably a reasonable tangent line as it crosses down here at negative 50. That's a poor drawing, sorry about that. But anyway, the other one's going to be super simple because the slope is 0, so it's y minus 1 equals, you technically want to write it, I guess you could go 0x minus 2. The 0 kills everything on this side, so of course it's what you expect, and you just get y equals 1. So the other tangent line is just going to be this guy right here, which if we graph those, I think we're going to see that it works out. You could put them in there, but you can see y equals 1 is going to be perfect there, and this guy you could guess our other one should match. Alright, let's see what else we can do. So in this example, we're going to determine where a parametric curve is concave upward or concave downward. We'll just look at both. It says concave up, but we'll do concave up and down, I think, and see what happens with that. So, hold on one moment. Alright, so first we need to compute the second derivative, right? If we're going to look at concavity. So I think we need dx dt, of course, first. So it's going to be really simple. Let's just eat t. We'll need dy dt, which is going to be a product rule. So we've got the first times the derivative of the second, which is going to be negative e to the negative t plus the second derivative of the first, in this case, is 1, so I'm going to clean that up and say I'm going to factor out an e to the negative t, so that's going to be negative t plus 1. I don't know if I'm going to use that factored form or not. Anyway, let's have a look. I guess I'll leave that space. Well, we'll leave a little space up in the top corner to sketch our curve once we put it in our calculator here in a moment. But let's find the first derivative, dy dx. So we're going to go this on top, and dx dt on bottom, of course. So it's going to be e to the t, and there looks, you can see the reason that I did simplify there is now I'm able to do some cancellation. Well, I shouldn't say cancellation, because this e to the negative t is really going to be down here. So, I mean, I have some options. I could say on top this is 1 minus t, right? And on bottom I have e to the t, e to the t. So just to be real clear about that, that's going to be 1 minus t over e to the t plus t, which is, of course, 2t. So if you want to write that as e to the negative 2t, you can. I think I just will, because that's going to be nice when I need to take another derivative here in a moment, because we're going to look at concavity, right? So I guess I'll do that down here. So we're going to go d squared y over dx squared. It's going to be the derivative of that, so I'll need another product rule, and that way I avoid the quotient rule as well. I don't know, it doesn't really matter to me, but we're going to go first times the derivative of the second, which is negative 1, plus the second times the derivative of the first, which is negative 2e to the negative 2t with my chain rule. And then I'm going to divide by the bottom squared. No, let's remember what we're doing here. This kind of looks like a quotient rule, but remember I took the derivative of this on top. That's what this is. Let's make sure, in case you're watching this video and haven't already watched some of the other ones or haven't done a lot of second derivatives in parametric, this is d dx of dy dx. Okay, that's what's on top, and then on the bottom we just put another dx dt, or another e to the t, in other words. So let's see if we can simplify this, because we're supposed to be checking concavity, and concavity of course is going to change where the second derivative is either 0 or undefined. So let's simplify. So on top I have a negative e to the negative 2t, and then I think I'm going to distribute here so I can get some like terms maybe. So let's see, we're going to have negative 2e to the negative 2t, and if I distribute it to this one, so I'm doing both of these, right? I'm going to have positive 2t e to the negative 2t, and then I'm going to be all over e to the t for dx dt. Yeah, I think I'm going to be able to combine some like terms up there. These are both like terms, that's negative 1 of them and negative 2 of them. Should be negative 3 of those. And this one's not a like term because it has that extra t in it. But I think I might be able to rewrite this a certain way. So let's put this on top. Let's say that that's e to the negative t. Let me get my eraser up here. So let's see. Let's put that up there and see if that makes much of a difference. I think it will. So we're going to put this whole thing times e to the negative t and see what happens with that. So now I'm going to distribute that e. I guess I'll get a different color here. To distribute that to both of these terms and see if I can shake some stuff up. So here I'm going to have negative 3. Then if I distribute it there, I'm going to have e to the negative 2t times e to the negative t. You add the exponents, right? So it's going to be e to the negative 3t. And then here I'm going to have plus 2t e to the negative 3t. So now I can definitely factor that out. I don't know if that was the best choice. I think I could have gone another way. I'm not going to distract you with that though, because now this factors out. So I have negative 3 plus 2t, and that's going to be easy to see where that is 0 or undefined. So I'm going to write it as negative 3 plus 2t, and now I'm going to move this guy back to the bottom, because now I can see the top is 0 clearly where this is 0. That's easy. So that's going to be 2 3/2. There we go. So there's one place where I might get a change in concavity, and then I also need to, of course, investigate where the bottom equals 0. If you remember your library of functions from Algebra 2 or wherever you learned it, this is an exponential function. That 3 is just some kind of, well, actually, so let's just go through it again. So what does that 3 actually do? It's inside of the function, so that means it's of a horizontal persuasion. It's multiplied, so horizontal type transformations are always opposite. So you'd think it would be a stretch, but it's actually a horizontal compression. So horizontally, we're going to be pushing it this way and this way. So it's actually going to get steeper vertically. But regardless, this is of course never 0 because there's an asymptote down here that it never approaches. So I don't even need to worry about that. There is no t. There's no t for this. So I think I only have one concavity inflection point number that I need to be thinking about, which is nice. So I can come up here and get a little chart going, a concavity test. So I'm going to say F and F double prime. I don't really have F here, but you get the point. And we'll say T equals 3/2 or 1.5. And we can pick some test values. Okay, so let's pick some test values. We could say T equals, I don't know, 1 on that side. That's nice. And T equals 2 on this side. Okay, so let's stick those into our second derivative. Now, where is our second derivative? Well, of course, it started up here. Then we simplified it to there, and to there, and to there, and to there, and to there. I think you can use whatever you'd like. I'm going to use this part of it right here because I like that one. So I can clearly see the top and the bottom. So let's see what we get. I'll use red. So if we put 1 into the bottom, of course, we're going to have positive on the bottom there. So if we put 1 on top, it's going to be -3 plus 2. That's negative. So overall, this region is negative. That means the function is decreasing, or the parametric equations in this case are decreasing. Oh, wait a second. I'm not doing the first derivative test. I'm doing the concavity test. So that means it's concave down. There we go. Okay, so now if I put 2 in on the bottom again, it's going to be positive. And then on top, it's going to be, what, -3 plus 4? Well, that's positive. So that means overall it's positive on the right-hand side of 3/2, which means it's going to be concave up over there. So now I think I'll just get my text out and write a little sentence. They asked where is it concave up, so I'm going to say this set of parametric equations is concave up on the interval t is, I'll get my equation going, t is greater than 3/2. Or you could put interval notation and go 3/2 with a parenthesis, of course, out to infinity. And on the AP test, you'd always, of course, want to justify yourself. So the sign chart is great evidence, but I don't think they take that anymore. They did when I was in high school, but they don't now. So it's concave upward on that interval because they like to see things like this. Because, and you can write it in symbols. So because F double prime. Since there's no F here, I don't really want to talk about that. Let's say because the, let's write it like we had up here over here. So I'm going to say d squared y over dx squared is positive, let's say is positive for that region. Okay, there's another good example. So in this last example, I thought we'd look at another problem where we check for and find spots where we are horizontally or vertically tangent to a parametric curve, and then we'll go ahead and check it with our graphing utility. So I think first, let's just look at our graphing utility first. So I think I already plugged this guy in. You can see it's in there already. 3 cosine of the parameter and cosine of the 3 times the parameter. Or not 3. Anyway, you see it. So let's go to the graph. And I think I set my window and went from -10 to 10 and checked to see that I was seeing all of the curve. You could, of course, change this to negative, not pressing that negative, pressing the little negative. TI calculators are so wonderful sometimes. And we could check and see if we could see more of the curve. You can see it kind of just traced back onto itself. So it looks like from the picture that we only have a couple horizontal tangent spots. Doesn't look like we have any vertical ones. I wanted to remind you at this juncture that in problems like this one or any other problems like the last problem, you always want to check to think about your domain at the beginning and the end of a problem and just kind of think as you go, are there any restrictions? So here, so far I don't see any restrictions. Like you can put pretty much anything into cosine, but if you have functions from your library of functions here that do have restrictions, like denominators that could be 0 or insides that could be negative, like inside a square root that could be negative, just watch out for those, or like the one we did in class, the logarithm problem that we had to think about at the very end. So that's fine. So we have an idea that we're going to probably get 2 horizontal tangents here. We'll just see what happens though. Alright, so first I think I need to find the derivative and set it to 0 and set it to undefined possibly, although hopefully that's not going to happen because we didn't see any vertical tangents. So dx d theta this time is going to be pretty easy. That's negative sine of theta, and dy d theta is going to be a nice chain rule in there, negative 3 sine of 3 theta. Right, so the actual derivative will be the ratio of those. So that's negative 3 sine of 3 theta over negative sine of theta. I think I'm just going to get rid of those negatives right away. They cancel out. Nice. Okay, so that's the derivative we're looking for. So at this point you might be tempted to try to break down sine of 3 theta like I am and say like, oh yeah, that's sine of theta plus 2 theta, and try to use some identities, maybe like, sine of theta. I think this one is a summation identity that's mixed, so you go like this, Hopefully you know what I'm talking about here, and I think this stays the same. Then you're going to have to expand these with double angle identities, and really, what's the whole point? Because remember, you're just trying to see where the top is 0 or where the bottom is 0. Where the top is 0 will produce possible horizontal tangent spots. Where the bottom is 0 will produce possible vertical tangent spots. You could also have a cusp or corner where the derivative doesn't exist, of course. And we didn't see any of that at all in our graph. Of course, we have the luxury of having a graphing calculator. But you want to definitely take advantage of that. So I don't think I'm going to have to worry about the bottom too much. We'll just have to see what happens. This looks pretty simple, so is this problem going to be over really quickly? I don't know. Let's see. So if we set the top equal to 0, you can just divide your 3, and that just goes away right away. So we get that. I'm going to shut down my calculator here. Kind of looks like we have one, by the way, for cheating at like 1/2 negative 1. We'll have a horizontal spot. That'll be one of them. And then we've got another one symmetrically over here. So I'm just going to close that down so we don't have to consume as much. My computer's already heating up. Alright, so solving for theta. So we've got 3 theta equals the inverse sine of 0. So that says 3 theta, and let's think about inverse sine. So where is the y-coordinate 0? Inverse sine lives here traditionally. So I think that'll happen here at least, because it's 1, 0 there. The y is 0. So that's going to be 0. So we get theta equals 0 over 3 is 0. Oh yeah, so they asked us, of course, to find the points on the curve. That's not a point on the curve, that's where the parameter makes that happen. So I put this back into the curves, and I'll get cosine of 0, which is 1, from that right there, right? And then I'll have cosine of 3 times 0, which is also 0, which is 1. So that's going to be x, and that's going to be y. Now, wait a second, because a second ago, I think on the graph, I shut it down. I didn't see a spot where it was horizontally tangent at 1, 1. It was like down in the 4th quadrant. So something's wrong here. Let's see. This is, I think, one of those sneaky domain issues that I mentioned at the beginning. So it didn't have anything to do with the original parametric equations. And nothing happened here. Theta equals 0. Oh, look at this. See, this problem has an issue right here. Remember, we didn't see any vertical tangent spots, and you've got to think about where this... So you have to also think about the domains of these guys as well. That could possibly cause issues, and on this problem it has. So I think we're good here, but this guy, are we good on? I think the answer is no, because dx d theta, if you put theta equals 0 in there, you go think about it over here again, right? That's negative sine of 0 degrees, which is going to turn out to be 0. So you're going to get a 0 on the bottom here. If you divide by 0, that's going to cause a problem. So even though the top would have a 0 at 0, it'd be like 0 over 0, and that's a problem for sure. So theta equals 0 is not going to work. Okay, so that none of that stuff is going to work. Let's just erase that junk right there. So theta equals 0 is not going to work. Well, we didn't do anything wrong, and there were definitely some spots where this was horizontally tangent. So just use your knowledge of trigonometry, and I've got an idea. So won't the sine, even though this is the actual arc sine value, of course, if you think about this, wouldn't this actually, like in pre-calc or whatever, be 3 theta equals 0 plus, and then wouldn't it happen again right here, and then again right here, and then again right there, so it'd be plus pi k, right? So this is one of those times where you've got to think about the other possible options that you have. So yeah, we're totally going to have some other options. So I think the next spot is going to be right there at pi. So it's going to be 3 theta equals pi for the arc sine of 0. So that's going to be theta equals pi over 3. Let's see if that messes us up. Well, of course, the sine of pi over 3, if we think about that, let's just get a little guy going here. Pi over 3 is 60, so this is root 3, 1, and 2. Sine of pi over 3 is going to be root 3 over 2. We're going to be good to go. It's not going to violate that anymore, and I don't think it's going to violate anything else. So I bet this is going to be one of them. So let's do that one. So this is going to be one of our horizontal tangent locations. So we're going to say x equals the cosine of pi over 3. And I'm going to just pull that off this triangle over here, adjacent over hypotenuse, 1/2. I remember it being at 1/2. That sounds good. All right, so then y is going to be the cosine of 3 times pi over 3, which is just pi. And so that's the cosine, so that's the spot over here, right? So the x over there is -1. Yes, totally. That's that spot we saw. Do you remember it looked kind of like this? This spot is 1/2 -1. That's where we have a horizontal tangent line. Great. Okay, so now I'm going to think about another spot. So we have another one. 3 theta equals, so we did 0, we tried pi. Next spot would be 2 pi. Let's try that one. So if I go 2 pi, then theta is going to be 2/3 pi. Is that going to violate this guy? Because we can't have this guy be 0. We'll get a 0 when we divide for our derivative. So let's see. So sine of 2 pi over 3. No, it's going to be some kind of ratio. So let's just show where it's at. 2/3 pi is here. 60. That's going to be square root of 3 then. 2 and -1. So sine to be square root of 3 over 2 again. So we're good. Check. Let me get rid of all this other junk out of the way here. Okay, so 2 pi over 3 is going to be another thing that probably works. Let's see if it gives us a different point. So that's going to be x from our parametric equations is cosine of 2 pi over 3. Good thing I drew that triangle. Just thinking ahead a little bit there. So the adjacent is now -1/2. There we go. Okay, so the adjacent over hypotenuse, I should say, is -1/2. So that's going to be cosine 3 times 2 pi over 3. So that's going to be cosine of 2 pi. Cosine of 2 pi is right here. The x-coordinate is 1. So that says the other spot where we're horizontally tangent is -1/2, 1. This first spot, I guess I could have written in normal Cartesian coordinates. So does that look right? That this guy could be -1/2 from symmetry? Yeah, totally. And up there at 1, it's obviously at that spot. So I think that we're good. So these are the two spots of horizontal tangency. Where is it going to be vertically tangent? And I think that the whole issue that we run into in the first place kind of tells you why there's no vertical tangencies. That would be where sine of theta equals 0, but we discovered that would be at theta equals 0, or it would then, of course, possible at 2 pi or 2 pi or 3 pi, etc. But these guys were here. that one being there, that one being there, and I bet 3 pi goes back to this same spot, and 2 pi goes back to that same, or excuse me, 4 pi goes back to that same spot, and so on. And of course 0 is going to lead to this 0 over 0 problem. So that's kind of a proof that it's not going to happen. The only other place it could happen would be out here further along, right? Out here at like 4 pi. But like I said, I think that's just going to be another spot where we're horizontally tangent again. Just like when we were retracing the parametric curve when we saw it at the very beginning. Right, I think that's going to wrap up this set of examples. I hope you found them useful and have some fun with parametric calculus. See you next time.